Hello students, good morning everyone. So I am starting with my lecture. In previous lecture, you have learned about the dimagnetism, and we had seen that dimagnetic material has pair of atoms, pair of electrons in the atom whose magnetic moments are in opposite direction. So the magnetic moment cancels pairwise and atom does not have the magnetic moment, and hence material also does not have the magnetic moment. So that is a peculiarity of the dimagnetic material. So the atom does not have the magnetic moment, so the material does not have the magnetic moment, so there is no magnetization. But if this dimagnetic material is kept in the external field, then it gets magnetized in the direction opposite to the external field. It gains the magnetic moment, so it gets magnetized, but in the direction opposite to the external field. Now in this lecture, you learn about the paramagnetism and ferromagnetism. So let us consider what is the origin of the paramagnetism. The dimagnetism, that magnetic moment, was because of the orbital motion of the electron. Beside orbital motion in the atom, electron also spin around itself. So spinning of the electron produces the current, and that produces the magnetic moment. So in the atom, electron of an atom, the magnetic moment is due to orbital motion as well as the spin motion. In dimagnetic material, the contribution of the spin motion is negligible. Only the contribution comes from the orbital motion. But in the paramagnetic material, the contribution also comes to the magnetic moment from the spin of the electron. So the magnetic moment is a vector quantity. So the total magnetic moment is a vector sum of the orbital magnetic moment and the spin magnetic moment. So this is another difference between paramagnetic material and dimagnetic material. In dimagnetic material, only orbital motion is responsible for the magnetization. In the paramagnetic material, beside the orbital momentum, the magnetic spin momentum is also responsible. Now, in this diagram, we have represent this arrow, this one. This arrow represents the magnetic moment of an atom. So magnetic moment of the atom in the paramagnetic material is not zero. It is a non-zero. In dimagnetic material, it is zero. But now more arrows are shown here. That is the magnetic moment of the different atoms. Now here, in the paramagnetic material, each atom has a magnetic moment, but the magnetic moment of the different atoms are oriented in the random direction. Number of the atoms are very large and they are oriented in the random direction. That means you will find that for every atom having the magnetic moment in one direction, there will be another atom whose magnetic moment is in opposite direction. So they will cancel. So the total magnetic moment of the paramagnetic material is zero. So although atom has a magnetic moment, but total magnetic moment is zero. That means the paramagnetic material is not magnetized. There is no magnetization. But when it is kept in external field, so now you are keeping in the external field, this external field you are keeping in the external field, then as you have seen in your lower class, maybe in 12th standard, when you keep a magnetic dipole in the external field, then it experiences the torque and it rotates in the direction of external field. So same thing happens here. This dipole moment will try to rotate to align in the direction of magnetic field. So as this magnetic field increases, the orientation also increases. So at certain value of the external field, at a certain value, all these magnetic moments are aligned parallel to the external field. And now it gains the magnetic moment. So total magnetic moment now is not zero. So the substance will get magnetized. But one more factor is there, is the temperature. If you increase the temperature, then there is a de-alienation. It gets randomized. So if the magnetic field is sufficiently high and temperature is sufficiently low, then what will happen is all the magnetic moment will align in the direction of external field and it will get magnetized. So now what happens is the magnetization in the direction of the external field. So if you keep this paramagnetic material in near the bar magnet, it will get attracted because the magnetization in the direction of the external field. But if you switch off this external field, if you switch off this, that means if you remove the magnetic field, if you take the paramagnetic material out of the magnetic field, then it will get randomized. Again, the thing will be like this. Similar, this thing will happen. So magnetization will become 0. So as long as it is in the external field, it will get magnetized. If you take it out of the external field, it will get demagnetized. So magnetization will be 0. So resultant magnetic moment is 0. Now let us see the theory behind this. This theory of the paramagnetism, actually what I explained previously is a qualitative, just description. But the description is from what is called as the Langevin's theory of the paramagnetism. Now this theory given by the Langevin, it was simply represented to you in a simple way, qualitatively. But that what I had mentioned in the previous slides, that was mathematically found by scientist known as the Langevin. It is called as the Langevin's theory of the paramagnetism, and it results into paramagnetic susceptibility, expression for a susceptibility. But this Langevin's theory of paramagnetism is a bit complicated. It requires a lot of mathematics, and you will not find this theory in detail in your textbook. So theory is beyond the scope of the at the graduation level. So you will not find it you will not find the theory in detail in the textbook, and you will find it in the research papers. Research papers is there. So here what is done is only few points are mentioned, and you will find in the textbook these few points, because the detail is not possible to treat it here because it requires a little complicated mathematics. So now here I will just mention the steps which are there, and same steps you will find in the textbook. So details you will not find in the textbook because of this complexity. So first of all, you take a material composed of entirely one molecular species. One molecular species. That means a material, all atoms, molecules of the materials are of the same type. Same molecules are present. Now each molecule having the magnetic moment m0. So magnetic moment is m0. And then what is called the fractional orientation. The fractional orientation means the direction, orientation in direction of this magnetic moment of a given molecule. See, fractional orientation is the direction as compared to the external field. So the direction of that magnetic moment is given by what is called the Langevin's function. Now this was mentioned to you. in the electrostatics. Similar thing were also there in the electrostatics. And that Lagrange function is written as y. It is m naught. M naught is the magnetic moment of the a given molecule. Mu naught is the permeability of the free space. Hm is the magnetic intensity, molecular magnetic intensity. Molecular magnetic intensity means intensity which is responsible to magnetize that given molecule or atom, divided by K. K is a Boltzmann's constant. Capital T is a temperature, absolute temperature. Okay, so this formula, in fact, a derivation is there, but it is beyond the scope of your syllabus. Then, from this, you can get a magnetization. The magnitude of the magnetization, it is given as Nm naught. Again, we are not deriving it. It is beyond the scope of the syllabus. Cot of y is the hyperbolic function. It's called the hyperbolic function. Cot of y minus 1 by y, where n is the number of molecules per unit volume. Then one can approximate this magnetization at any temperature above absolute zero, and as a vector form you can write it like this: vector m equal to m naught square by kt mu naught hm, and you'll find that. So you'll find it with a general expression for magnetization. Magnetization equals susceptibility to into hm. So this susceptibility is equal to m naught square by kt mu naught. So this is the formula for the susceptibility. You will find it is a positive. The susceptibility is positive because the magnetization of the paramagnetic material is in the direction of the external intensity. So this is what is called as the Lagrange theory of paramagnetism. Here only points are given and not details. You will not find detail even in your textbook. But actually, this theory is much more complicated and lengthy. Then next we go to third type of the material. The first type is diamagnetic material. That atom has zero magnetic moment. So material has a zero magnetic moment. In external field, it gains the magnetic moment in the direction opposite to the external field. This is a diamagnetic material. Paramagnetic material, the atom has a magnetic moment, but material does not have the magnetic moment. In external field, it gains the magnetic moment in the direction of the external field. Now, ferromagnetism. Let us see what is the ferromagnetism and what are the ferromagnetic material. The ferromagnetic material has what is called as a domain structure. It is a domain structure. Let us see what is the domain structure. Now, what is the domain? Suppose you have material like this. Suppose you have material like this. Then what you will find is, in the ferromagnetic material, it will have domains like this. Domains are there. Some region is there. Some region is there. And those regions are called as domains. Now, what is the peculiarity of these domains? Now, in this domain, there will be group of atoms or the molecules. So, I am writing the arrow for the magnetic moment, having the magnetic moment in the same direction. So, there will be group of the molecule or atom having the magnetic moment in the same direction. So, similar type of the molecules will be there. Here, in the neighboring one, there will be group like this, but they will have the same direction, but their direction different from that neighboring one. So now this is the domain. Now what happens is this group acts as a one unit. Now the ferromagnetism is due to a spin. The orbital momentum does not contribute to the ferromagnetic magnetic moment. Only the spin. We will see that little later. See, the diamagnetic material, the magnetic moment arises because of the orbital motion. Paramagnetic material, the magnetic moment arises due to the orbital motion and spin motion. Ferromagnetic material, the magnetic moment arises because of the only spin motion. There is a theory behind that. Now, all these molecules or atoms, group of this molecule, in fact, the volume of this domain is about 10 raised to minus 6 meter cube. 10 raised to minus 6, very small, 10 raised to minus 6 meter cube. Now what happens is, because of some reason, all these molecules or atom, they will act as one group. So in atomic physics, we call it as a coupling. Coupling will be there. It is called as a spin-spin coupling or SS coupling. In atomic physics or molecular physics, you can come across what is called SS coupling or LS coupling, SS coupling, JJ coupling. This is SS coupling. SS coupling means spin. Because the similar spins of the different atoms or molecule, they act as a one unit. So they act as a one unit. So this is the domain. So in the domain, all the molecules or the atom have the magnetic moment as the same direction. This magnetic moment is contributed by the spinning of the electron, and all this group will act as a one unit. It will act as a one unit, and that is called as a domain. The neighboring one, similar thing will be there, but the direction will be different. Neighboring one, similar will be there, but the direction will be different. The direction will be different. And you will find that different domains are aligned in the random direction. So for every domain, see, suppose you draw it like this. Suppose you draw like this. I can show like this here. All these magnetic moment, I can show it as one unit, like the one. Here represented by one arrow. Here represented by another arrow, and so on. So these are randomly oriented. So what happens is, for every magnetic moment of a given domain in one direction, there will be another domain having the magnetic moment in just opposite direction. So pairwise magnetic moment will cancel. So the total magnetic moment of the ferromagnetic material will be 0. So it is not magnetized. So like iron, a piece of iron, it is not magnetized. It does not produce the magnetic field. So iron, cobalt, steel, nickel, this material, they have a domain structure and they are not magnetized, although the domains are there, magnetic moment is there, but they are randomly oriented. So the magnetization is 0. Now when you keep it in the external field, see what happens is, when you keep it, that in the external field, you apply the external field. You apply the external field. Then what will happen is, all this domain, see all these domain, magnetic moment will experience the torque in the direction of field, and they will try to rotate. Now what happens is, suppose this is rotated this way and this is rotated this way. Then what will happen is, there will be coupling between these two domains. So this will become bigger domain. See, now what happens is, if you increase the magnetic field, then the magnetic moment of each domain will get rotated. Now it may happen that this domain, and this domain both have the magnetic moment in the same direction. So they will couple together to form a single domain. So this is called as the growth of the domain. So domain grows. And for a very large, large magnetic field, see, if a material is there, for a very large magnetic field, very large magnetic field, extramagnetic field, all the domains will be aligned in the same direction, and then it will form a one single domain. It will get magnetized. So single domain. Now what happens is, if you take this, if you switch off this field, or take the material out of the field, then what will happen is, the two things, one thing what will happen is, it will get randomized, but will not get completely randomized. It will retain the magnetic property. So the magnetism will be retained, as we have seen in the hysteresis. So if you remove this ferromagnetic material out of the external field, then what will happen is, complete randomization as it was originally there will not be there, but it will remain some magnetic moment. So it will get magnetized. You can make it into permanent magnet. Now, how much it will get randomized depend upon the material. Certain material, they get randomized to a large extent, like soft iron. It will retain very little magnetic moment. But there are materials like steel, cobalt. If you keep it in the external field and if you take it out, then most of the magnetization it will remain. So it will retain. Then you can make it into permanent magnet. Then one more thing is, now here what we have seen, see I have shown here, this here. See this direction like this direction like this. Now what happens if you see the boundary of this boundary of the two domain, it won't be sudden change in the direction. It won't be sudden change. So at the boundary between the two domain, this magnetic moment will be slowly change the direction from this to this. Now it happens in about 100 atoms. So this boundary suddenly at the boundary the direction does not change, but over some width of this boundary, the direction of the magnetic moment from atom to atom will change. In 100 atom, it will change from one direction to the other direction. This boundary of the domain is called as a block wall, or it is called as a domain wall. Domain wall. It is called as block wall or domain wall. Now it is shown here. Here you will find that unmagnetized single crystal like this. See, this end is opposite direction, this end is opposite direction. Total magnetic moment is 0. Polycrystal here like this. So randomly directed. So total magnetic moment is 0. And here this block wall. See example, this block wall is shown there, shown here. This is a wall. So there will be slowly rotation from one direction to the other direction. Then it is shown here how they get magnetized in the external field by what is called the domain wall motion. So domain become bigger. Then by domain rotation. So every domain magnetic moment will slowly rotate. So these are the different diagrams. Then we go to a theory of ferromagnetism. Now this theory of the ferromagnetism were given by different scientists. Again, it is much complicated theory. Detail is not there. In your textbook, you will not find a detail of that. Only certain points are mentioned. So I will also mention those points. So actually the mathematics of that is much complicated. So that's why it is not explained in your textbook. It is beyond the scope. Mathematics is beyond the scope of the graduation level. So now here, in the domain, there is the alienation of the different magnetic moment. See, there are group of molecules having the magnetic moment in the same direction. Now this Hm is what is called as a molecular magnetic intensity. Molecular magnetic intensity means magnetic intensity responsible to magnetize that molecule. Now this H is that external field. Example, if you keep it in the solenoid, that H equal to Ni, this is the external field, and M is the magnetization. Now for a certain material, they have found like, now this example is taken of for a certain material, vector Hm equal to vector H plus 1 by 3 M. Okay. How it is obtained, we are not giving it here, it is beyond the scope. Now here, see, now what we are looking here is how the ferromagnetic material get, first of all, it has a domain structure, and how it will get, how that domain is permanently magnetized. See, domain is permanently magnetized. It has a magnetic moment. Now here, for permanently magnetized, even in the external field, so if the external field is also not there, then it is magnetized. Now Hm is 0. For Hm equal to 0, molecular field is 0. H has to be 0, M has to be 0. So M is 0 means what? Magnetization was not there. So that means magnetic moment is 0. So the Hm cannot be 0. See, Hm cannot be 0. See, Hm cannot be 0. So now here, see, Hm is not 0, but what is 0 is H. External field is 0. Suppose you take material and keep it in the solenoid. You take it out of the solenoid. What happens is H is 0. When you take it out of solenoid, H is 0. But what happens is, still, that material has a magnetization. So that is because of the molecular magnetic intensity. Then, now initially it was done for 1 by 3 for certain material. Then, it was generalized for different material. Instead of taking 1 by 3, it was taken gamma. So, external field is 0, Hm equal to gamma m. So, a material which is magnetized, Hm equal to gamma m. Then, here, a different concept is used. And one condition is found. I will not go through it, not required also. See, this condition is found here. And this condition is a condition for the occurrence of the ferromagnetism. Now, this Hm equal to gamma m is called as, this is called as a vis molecular field. Now, it is found that this gamma is very large. Gamma is very large. For a ferromagnetic material, the gamma is very large. So, magnetic field produced by a ferromagnetic material is very large. The scientist Weiss was not able to explain it. So, it was explained by a scientist known as Heisenberg. Now, Heisenberg showed that, again by using a derivation, he shows that only spin magnetic moment is responsible for the magnetization, permanent magnetization. That is one thing. Other thing is, the field produced is because of the electrostatic force. So, two things. One is the spin magnetic moment, a spinning of the electron. Other is the electrostatic force between that electron. And he used the quantum mechanics, what we call it as a wave mechanics. He used the quantum mechanics. And he showed that, we'll see that in the later on in the diagram, the spin of the neighboring atoms can change from parallel to the antiparallel. This we have to see. And when the spin changes from parallel to antiparallel in a given domain, spin changes to antiparallel, simultaneously there is a change in the electrostatic distribution, electrostatic energy. And this certain electrostatic energy, we'll see that detail a little later, it is responsible for the ferromagnetism. And this is how, now this theory is called as a Weiss-Heisenberg theory. Then, that Weiss-Heisenberg theory, they found the expression for the magnetization. The two different formula they got. And to find out the magnetization at particular temperature T, you can find it by using the graph. See, graph is drawn, magnetization against Y. If you plot a graph of magnetization against Y, if you use the first equation, then you will get a curve like this. If you use the second equation, you get a straight line, because according to the second equation, see, the magnetization is proportional to Y. See, K, gamma, mu naught, m naught is constant. You will get a straight line. For different temperature, the slope will be different. So now, see, for a ferromagnetism, there are two expressions for a same quantity. So now, to find out what is the magnetization, you draw the graph, the point where it intersects, that is the value of the magnetization at the temperature T. Suppose, if you increase the temperature, suppose you increase the temperature, then slope of this will increase. So, slope of this will increase. So, you will get a graph like this. So, what will happen is magnetization will get lowered. Lower value of the magnetization. Now, suppose this temperature is increased to such a temperature that this line becomes vertical. Then what happens is, see, the magnetization is 0. So, magnetization disappears. This temperature is called as a Curie temperature. So, that means what happens is, suppose you take a ferromagnetic material, you heat it, higher and higher temperature, magnetization will become less and less, and at a certain temperature, then magnetization is lost. And that temperature is a Curie temperature. And above this, a spontaneous magnetization vanishes. and what happens is a domain structure will disappear, and it will behave like a paramagnetic material. Okay, that is a part of that Weiss-Eisenberg theory. Now here we have drawn that. See here we have drawn. See in a given domain, all, as I mentioned, that all magnetic moments are aligned in the same direction. All magnetic moments are aligned in the same direction, and there is a coupling. So that is a ferromagnetic material. This is a ferromagnetic material. So a domain has a magnetic moment, and domain has a strong magnetic moment. There are some materials where these magnetic moments are there, but there is a pair of the magnetic moment in the opposite direction. So magnetic moment of that domain will become zero. That is called as an antiferromagnetic. It is not a ferromagnetic material. It is an antiferromagnetic material. Now in that domain, what happens is this magnetic moment, pair of magnetic moment will be in opposite direction. So total magnetic moment is zero. So it does not produce the magnetization. So it is called the antiferromagnetic material. Then there are some materials where, and they are also very important, there are a pair of this will have the magnetic moment in opposite direction. So it is one direction, the opposite direction. It is one direction, opposite direction. But value will not be equal. So it will not become zero. Pairwise, it will not become zero. So the magnetic moment of the domain will not be equal to zero. So they are called as a ferrimagnetic, or they are called as a ferrite. So there are three categories of material where domain structure is there. In one, all the magnetic moments are aligned in the same direction. That is called as a ferromagnetic. Then the pair of the atom or molecule have the magnetic moment in equal but opposite direction. So magnetic moment is zero. That is antiferromagnetic. And there will be pair of the atoms or molecules having the magnetic moment in opposite direction but of the unequal amplitude. So magnetic moment will be there, and they are called as a ferrites. And this is what is mentioned here, ferrite. So I mentioned here about a ferromagnetic material, and why it is ferromagnetic or antiferromagnetic or ferrimagnetic, and that is because of the energy. Because of the, as per the Heisenberg's theory of ferromagnetism, there is a change in electrostatic energy with the associated with the change in parallel to antiparallel parallel spin. And if the parallel alignment, then ferromagnetic, antiparallel alignment, antiferromagnetic, and unequal magnitude is ferrimagnetic. Now this ferrimagnetic, say, they are very useful, and mostly they have a structure of this type. See, oxygen is there, iron is there, here O3 is there, and M you can replace by any material, cobalt, nickel, magnesium, copper, and so on. All these compounds are called as the ferrites, and they have properties. One of the properties, it has a spinel structure. Spinel structure. Now, spinel structure is a crystal structure. Spinel structure is a crystal structure, and in this crystal structure, all the molecules which are there, what is called as these lattice points, what are called as lattices, that will be having the same type of the molecule. Then it is called as the spinel structure. It is a crystal structure, but all these corners will have, or the what are called a lattice point, will have the molecules of the same type. That is spinel structure. And these materials have the large saturation magnetization. Magnetization will be very large, but see, that means it will be a strong magnet, but poor conductivity of the electricity. These are as far as it will be a very strong magnet, but electrically it will be poor conductor. So because of this property, it is used. Because of this property, it is used for the high frequency operation. Now we know that the frequencies of the very high, and if you keep that material in that high frequency, then it produces the eddy current. See, eddy current. You might have studied earlier what are called as eddy current. So eddy currents are produced, and these eddy currents are harmful for any device. So now what is done is that material, core of that material is taken of the ferrite material. So because the ferrite material, it will get magnetized, strongly magnetized, but electrical conductivity will be very poor. So eddy current will be produced to the minimum extent. Okay, so these are what are called as a ferrite. So this is what I am to take it for this today's lecture. Now next lecture I'll take it on the Monday. Next lecture I'll take it on the Monday, and on the Wednesday I'll give the online test in this paper. The portion for this will be first chapter, same was which was there earlier. Written instruction I'll be sending you. Thank you very much.
Thank you, sir.
Welcome.